Thanks for the invitation. So I will tell you about commensurating actions of groups of birational transformation. And it's talk based on start with Serge François. And there are two topics that we have to put together, which is commensurating actions, which is part of basically of geometry group theory, and groups of birational transformation, which is out of algebraic geometry, birational geometry, which is a much older topic. And I have to start with one of these. And I will first start with some basic notions of algebraic geometry, which are more than 1 century old. Then I will tell you about commensurating actions. Then I will tell you how these things can be put together. So let's say x and y are irreducible varieties. They could be over any algebraically closed field, let's say over complex, because it's not more complicated otherwise. And basically it's enough to think of the case when they are either affine or projective. So irreducible Zariski closed subset of the affine space or the projective space is essentially okay. And in the affine case, when you define the morphism from a variety to another, you just define them as a restriction of polynomials. But sometimes you allow like poles, which what we call regular function on an open subset, is you allow to divide by polynomials that vanish only outside the open subset you take. And in this case, there is that natural notion, which is a birational map. X, so y is a regular function from U to V, where both so that's a fraction. So in this case, I can take y. So U is contained in X is a dense open subset. Dense open or non-empty open is the same. And always for the Zariski topology. And regular is like polynomial. And so it should be thought of on X, it would be given by a quotient of two polynomials, but the denominator should not vanish inside U. And a birational map is a regular function from U to V, but that's an isomorphism inside X and inside Y. An isomorphism between two dense open subsets. And of course, U and V are not part of the data. So modulo, in both cases, modulo coincident on non-empty dense open subset. Example. So basically are two kind of example where x and y are the same, but I start with just when you have different ones. For instance, you can have say finite space C2. You can map it into P2 of C, and you map xy to x y colon 1, and that's a birational map. Actually, it is regular, but the image is dense. But of course, in the other direction, it's not defined everywhere. But still, it's an isomorphism to an open subset. So it's birational. So in this case, we say it's a birational morphism because it is defined everywhere. But you can also map C2 into P1 cross P1 by mapping xy to x, just coordinate wise. And in particular, P1 and P2 themselves, they are birational. So in this case, you have such maps. You can write by composition. I don't know if I want to write them. It's not so. From P2 to x, y, z go to x, z, y, z. In the other direction, x, y, z, t will map to this thing there. X, t, y, z, z, t. X. X. It's just by substitution that you get this. Okay. So the idea is that I have when I work in the birational category, I have to choose a model, and sometimes the better model could be P2, sometimes P1 versus P1. And in the SQL, I will have to change the model with no control on it. So I have to consider all models of the same variety, and for some reason I will have to focus on the projective models. And so I have sometimes non-projective models which are nice to consider, but I will kind of singularize the projective ones. Okay. Let's when x equals y equals c to be d, as such a rational map. So for CD to CD is given by is always of the form x1 to xv maps to fi x1 xv fv x1 xv, where fi equals pi dot qi is a rational map, is in C1 D. I substitute, so T is not. It's fine. I substitute what I like. So okay. So these are indeterminate. These are numbers. That case there will be no condition, but then the condition that such a map would be birational is a non-trivial condition. it's if and only if actually it's birational, if and only if F1 Fd generates C, so is algebraically free over C and generate as a field.
Means that it has an inverse of the same form, right? This means that it has an inverse of the same form.
And say more. And in this case, we see that so the group of birational of X is a group of birational maps from X to X, and in this way we see that BS bar of C to D is equal to the automorphism of this field. So it's like a gamma group, but of course not in a context of algebraic extensions. And that's actually more general. It's always it is isomorphic to over C of X when X is affine. And these are and that's a ring. Actually, I don't. Ring of rational maps from X to C.
So, but basically, it's just the rational maps with rational inverses.
Mm-hmm.
Right.
Yes.
Yeah.
And that's always a finitely generated field over C, and conversely, every finitely generated field over C occurs as some variety, so it's part of field theory. But of course, the richness of algebraic geometry allows much more intuition than just working with fields. Okay, what should I say more? Okay, just to say, so okay, the idea is to study the structure of this group, and I will focus on, let's say, on the case affine or projective space, which is essentially the same. Saying that first, there is one case which is obvious or easy, standard, which is case D equals 1, because so per of C, which is also per of P1, and in this case there is P1 is kind of the best model, which means that its self-transformation are automorphisms. So this is out as a variety of P1, and this is PGR2. Yes, PGR2. So basically, it's once you have the best model, you just consider automorphisms. But on the other hand, per of C square will certainly not have such a form. It will not look like an algebraic group. Just to see this, let's see what will we see in it. You can see inside. You can. So it's isomorphic to bar of P2. It's isomorphic to bar of P1 plus P1. It's also isomorphic to bar of C2. Bar of P2 is isomorphic. It contains both P2, which is isomorphic to PGR3. Where P1 plus P1 contains both P1 plus P1, which is almost equal, so let's say it contains within X2 PGR2 cross PGR2. So of course, in the PGR3 and PGR2 cross PGR2 can be embedded in a common larger algebraic group, but not inside, actually not inside BRC2. They really fit like with some intersection, but not inside a larger one, algebraic group. And BRC2 is a big group which is it contains all C2, which is a better understood group, which anyway is infinite dimensional, because it contains, for instance, a big infinite dimensional abelian group of the form x, xy maps to x plus phi plus p of y, y, and p is a polynomial. One variable, so that's a big abelian group of infinite dimension.
Do bird of P1 and cross P1 and bird of P2 together generate a like a dense subgroup?
They actually generate the whole group. Actually, the BRC2 is generated by PGR3 and what's called the standard involution, which is it has the form x, y, z to 1 over x, 1 over y, 1 over z. Which you can rewrite as x, z, blah, blah, blah. That's called the standard involution. That's one generating set. And with this, it's easy to see that almost anything reasonable you add will generate anything. So okay, the idea is we want to study these groups which are quite complicated in general, and the idea is to try to find actions. What's the problem is that they are defined as groups with a natural kind of quasi-actions on the set of on C to the C square or C to the D, and which are not actions. So to find actions, you usually have to either to consider it as an automorphism of field, but that actually does not help so much in practice, or to make some limit arguments. And there have been a lot of works, especially by Serge Cantal, with this idea, which in the case of C2 have led to many results of guaranteed alternative, results of non-simplicity using common hyperbolic ideas, Hatzingen dual action things. But anyway, the case of higher dimension is more reluctant. There are some results, but it's really hard to have general results. For instance, except maybe C3, but in larger, there is almost nothing known about finite subgroups. We could expect that a big symmetry group cannot be embedded into C4, but I think it's not. It's still plausible. It sounds crazy, but it's still plausible that C4 contains all finite groups. Everybody would conjecture it's not true, but it's unknown.
About algebraic groups, right? What is known is about algebraic subgroups.
But finite groups are algebraic groups.
Oh, big algebraic.
You mean connected?
Maximal rank or something.
Probably connected algebraic groups is usually much better understood, but yeah, connected algebraic groups behave better. But in algebraic groups, you know that if there is a finite group, it will act by automorphism on some model, but so far that does not help, because you don't have a classification of the model. Anyway, okay, let me make a break with geometry and talk commensurating actions. I have to struggle. Usually I will not denote the set as X, and that's a bad idea here. So I have to be careful, and you have to be. Tell me if there is X is not good. Okay, let's G act on a set E. So G is any group, and E is any set. It's completely abstract. And A inside E is any subset is commensurated. Commensurated by G if for every G A is like almost invariant, and that's one terminology as well. So A and its translates have finite symmetric difference. So this is sort of classical. It's important in Stolling's work and Baudry and so on. N. Okay, I will give many examples, but the first, what should we call the trivial examples? Of course, the invariant subsets have this property, and also if you perturbate an invariant subset by a finite set, you also get something invariant. And let's give this a name. I will not say trivial because trivial is always ambiguous in this case. Is transfixed if there exists a prime G invariant such that a symmetric A prime is finite. And the first thing is, how can you kind of recognize this? There is something special if you do this, is that this cardinality of the symmetric difference between A and GA, let me give it a name, A of G. It implies that it's actually bounded. Not only finite, but bounded. And the point is actually that the converse is true. That's purely combinatorial results, which was first proved quite crazily late in the 90s. Brailovsky, Prager, and Pazechnik. And with a kind of crazy proof, because the first proof is that you have an analogous notion for group actions with subgroups commensurating in the sense of groups, which means that you have the same thing but with the indices of the intersection instead of symmetric difference. And the result for groups was proved by Schlichting in 80. And well, it was a paper in German. 10 years ago there was a paper by Bergman and Elstra, which is better known in English with the same results. And the proof consisted of a reduction to the group case using with products. I mean, that's which gave kind of crazy bounds. And soon after this paper by these three authors in 96, there was a paper by Peter Neumann with a kind of more natural proof, giving also an optimal bound. Optimal means if I have a bound on this function, I want to find an invariant subset with a minimal symmetric difference with A. Okay. So the first example beyond this particular case would be Z acts on Z by translation, and A is N. And there is a kind of almost universal generalization of this, which is G acts on the Schreier graph. Let's say the transitive case. So here I assume that this is finitely generated. I think so. Finite generating subsets. So that I have a graph, and then for every A in E, A is commensurated if and only if the boundary of A is finite. And but it's transfixed in the transitive case only if A is finite or finite complement. So in this case, we see that all these notions are study of commensurating subsets is related to the to ends, and
Sorry, when you say the group act on the Schreier graph?
no, I don't say this.
Okay.
Yes, it acts. It acts on a set. But I don't say. I mean, it acts on the vertices of the Schreier graph. It doesn't preserve the graph structure. It acts on the Schreier graph with boundary displacement.
But you compute the boundary using the graph. But you compute the boundary of A using
The boundary. I mean, I have.
the edges that join
You choose the notion you prefer because I mean it's locally finite. You say the points which are inside who are neighbor outside or outside with neighbor inside or the union of both is not important because I just want to make sense of having finite boundary. So in particular, from this, there exists A commensurated and not transfixed. If and only if so that's called E of GH is more than 2. Say that E, I mean the Schreier graph E has more than 2 base. Okay, that's the thing. I will sort of go back to this at some point. There is something called L2 action. What is the L2 action? Whenever G acts on E, you first denote and A is in E, denote L2 A of E. It's a copy of L2 of E, but inside the whole set of functions. So it translates by the characteristic function of A, 1A plus L2 of E. We view this inside R2 to G, the set of all functions, where I just want this to have a natural action of G. And its invariance, this coset is invariant if and only if A is commensurated. And in this case, you get an isometric action. Affine isometric action on a Hilbert space. And actually, that's a very neat proof of this theorem, because once you use a fixed point, when you assume that this is bounded, you get bounded orbits here. You have a fixed point, and you easily get from this you get an invariant subset of Fermat distance. And I should say, so what this L2 action remembers essentially this length by saying that the distance between 1A and G1A, just the alpha distance is just equal to this length with a square root. One more point, there is a cubulation. So it's another kind of extrapolation of E, but more in kind of the L1 context than the L2. What you say, you consider the set of, so your vertices will be the set of E prime, of A prime, so B in E, such that B is close to A. B and A have finite symmetric difference. And that's and you make this a graph by joining B to B union little b, whenever B is not in B. You can even put a canonical orientation. And the structure of this graph is it's called a hypercube. It's full of squares because whenever you add to have B, you can add 2 points, B union B, B union C. And then you can, if B and C are distant and are not in B, you can add both. And if you add a third element, you can add it and you get cube. So there is a kind of visible way to cubulate. If you don't like to cubulate, you can just say that this graph is a median graph. I'll simplify this, but it's a way to, median graphs are the way to deal with quasi-cube complex without using cubes. So everything here is canonical, so there is a G action on this graph, and it completely remembers this because the distance in this graph between A and BA is equal almost by definition to A with no square root this time. So I mean this uses in the canonical way an action on a quasi-cube complex, and even better there is a converse. It's not so important here, but it's important if you just want to motivate this point of view. Every action of G on the quasi-cube complex that I won't define because it's sort of a parenthesis, and many of you know this, induces comments or family of commensurating actions. Actually, the set E is canonical. E will be the set of half spaces. In terms of vertices, these are the totally convex subsets whose complement is also totally convex. And A depends on a little choice. Is the set of half spaces containing some given V0 vertex. And you almost up to multiplication by 2, it will also preserve the distance. And that's even, in a sense, it's even more canonical than the previous one. The previous one was canonical, but yet it gives, in a sense, the worst possible cumulation you can get. For instance, if you start from here, from the action on Z, like on the quasi-cube complex, which is Z, which is kind of very small, and you go back and forth, you will get an infinite dimensional guy. In that, so sometimes the challenge when you tubulate is to find good subcomplexes that behave well, and then you need some habits, so some assumptions on the groups and so on. Okay. So there is natural property W for a group. So G, a group has property FW if for every commensurating action so I write it as GEA. To mean the act on E and commensurates A. The A is transfixed. And more generally, if H is a subgroup of G, GH has relative property of W if for every action of G, A is transfixed by the small group. Example? The example is the case when H is so when G is of any group, but H is a cyclic group generated by a single element which is distorted. Distorted, which means if G is finitely generated, it means that the word length of C to the n grows sublinearly. I can say it like this in general, even if G is not finitely generated. There is S finite such that the limit when n tends to infinity of the word length of Cn with respect to S divided by n is 0. And this implies that GH, GC has relative property FW. And this is a fact which in terms of classical proof was first shown by Haglund and also applied as a surprise when it's something very a posteriori, very immediate, especially with when you using commensurating actions, because basically you have to classify commensurating actions of Z, and it's not hard to you first have to reduce to actions with finitely many orbits. That's a general fact for finitely generated groups. Then you can reduce to the transitive case, and you don't care about finite orbits, so you will have only Z acting on Z itself. Essentially, the only non-trivial way to do something is to make is n of finite perturbation, and each such commensurating action will make a linear contribution to the function L. So it will grow linearly. So whenever it goes sublinearly, you force it to transfix. If I anticipate on if I use the equivalence point of view of cubulation, it means that whenever a group has a distorted element of infinite order, then it cannot act properly on the classical complex whatsoever, even infinite dimensional. Which was actually the way Haglund put it first. Okay. Anyway, that's using this, you can also have an absolute property SW can be used to show that SLG G for the at least 3 has property FW using bounding generation by unipotence, by exponentially distorted unipotence. And it also works in other cases where.
But this case, this follows from.
Yes, I will say property.
Oh,
yeah.
sorry.
It also works for something like SLD or the float of 2, but even for d equals 2. So as Massato said, there exists an important class of example which comes from property T. Implies property FW, and also in the relative case. And that just by contraposition is just a consequence of the canonical L2 action. And that's another and older way to prove that these groups have property FW, except the case D equals 2, which in this case has no, there is no, I don't know any other proof. And in this kind of lattices in a symmetric D group with all factors of rank 1, for instance, in the co-compact irreducible lattices, we don't know what happens about property FW.
Donc, pourquoi pas que la ici, on pourrait pas passer
So, I would say conjecture, if you have a semi-simple group, D group of rank at least 1, and you have an irreducible lattice, then it has property FW, and say rank at least 2, and irreducible lattice has a property FW, and it's known in property case, it's also known when at least one factor has property T, but when no factor has property T, it's only known in the only case where it's known are boundary generation, and there are cases where it's based on boundary generation. Yeah. So it's they are all non-uniform. So in the uniform case, it's never known. There are some Keller results saying that spiral graph has at most 2 ends or things like this. In special cases like SL2. And okay, I will state one. So equivalent is G is a group now. Following our equivalent, G has property W. Every action of G on a quasi-group is complex has a fixed point inside the cube, not necessarily in any completion. For many years I thought that this was true, but you would have fixed point inside the completion, and that was a difficulty for technical difficulty. But actually no, there is a fixed point inside the cube. We know it's not just using the fixed point property for bounded orbits. So there is something natural behind this result of Gerasimov. For each action of G on a median graph, the median graph, since I don't want to define them, I will just say that these are the one skeleton of S02 complex. There exists a finite orbit. I don't assume that the median graph is locally finite, and it is also equivalent to the same, but saying that there exists a bounded orbit. So in general, there can be valid orbits that are infinite, but there is one which is finite. And then even is one which is isomorphic to a cube. So here I assume G is finitely generated. Actually, a countable group with FW is easily seen to be finitely generated because it has property FA. Every paragraph graph of G has at most one end. And for those who like cohomology, for every E G set, H1 of G is function with compact support, with finite support, vanishes. That could replace Z with any torsion-free, non-trivial torsion-free evidence.
Last but one point says that it's enough to the transitive actions.
Yes, there is a reduction to transitive actions. I mean, there is one lemma for finitely, for this one, for finitely generated groups, that if you have a commensurating subset inside any action, then for all but finitely many orbits, the intersection of A with the orbits is invariant. Really invariant. So for all but finitely many orbits, nothing happens. That's not true. It's very easy to disprove in the case of a countable group.
Consider what this notation means. It is Z.
Function with finite support from E to Z. Okay, now I want to put things together. So how much time do I have? It's already
10 minutes.
okay. So I start with the say X projective variety. You can think of I would like to say you can think of the projective of Pn, but that's I will have to change it. So in a sense, it's simpler to be general representation. Anyway, I define each hypersurface of X as a set of hypersurfaces of X. I mean irreducible hypersurfaces of X. So let's construct an action of X on some set with a commensurating subset. And actually, the simplest to be defined will be not the E, will be A. A will be equal to the set of hypersurfaces. So what I should emphasize, when you, as I said, X does not really act, but quasi per X, which is equal or G quasi acts on X, also it quasi acts on its subvarieties. But the special feature of hypersurfaces is that there is only a finite exception of points where things are ill-defined. So that's the idea, is that there is something bigger where you would get an action. And actually there is some pure abstract nonsense which tell you that there exists such a set. And we could be very happy with this. The problem would be that if you do just this, you don't get any theorem behind it. So I need to sort of identify E in terms of basic algebra geometry. So how can I do this? I will have to make some kind of limit over blow-ups of x, even if I don't technically need blow-ups here. So the crucial point, if you have a birational morphism and x, y will also be projective, y to x. So birational morphism means it's a morphism, it's defined everywhere, but the inverse is just a birational map. So typically, if you know what's a blow-up, that's typical kind. You have some point and you replace it by a projective space of dimension n-1. And okay, anyway, the idea is from this you have you want to have an embedding from if x to if y. What you can do, you can say that you have a hypersurface here, you take its inverse image, but so I have x and my y have a hypersurface, and I take this inverse image and I get something. Maybe I have a problem of definition. Maybe I could even have something of in the inverse image. I could have some smaller varieties. First, because it's a birational morphism and everything is projective, it's surjective. So there will be at least one component of the good dimension. But then there could be some of these components that just go to a single point. And I don't want to take care of them, but there will be at least one which does not do this. So there exists, I have H, there exists a component which maps onto H. The point is that there could be two components, and I can give an example. If I have this, and I have what call it usual resolution, it's this projection, and it's curved, so hypersurfaces are points, and these points would have two pre-images. But that's a typical non-smoothness problem. So it's if S is smooth or even normal, and so I mean every hypersurface here, there is a unique hypersurface here whose image is exactly the hypersurface. So that's the first point. The second is just something saying if you have. So this shows that we need some smoothness, and that's technically.
So if you're just blowing up at some points, I mean, can you just sort of lift x in some obvious way, like follow it through the? If it doesn't go through the blow up points, there's nothing to say, and if it does, you just use a tangent plane. I'm saying, is it just an explicit construction? When x is smooth.
Of what?
When x is smooth, the component that projects to x. Or you all have, never mind.
So okay, one point is to have enough smoothness. We could, and then when you have a variety to find things over it which are smooth, it's for instance, it's known in characteristic 0, it's known in surfaces, but it's not otherwise. So that's why normality is a much more flexible framework. But anyway, what's important is to have enough nice varieties for this to go through. So you need something like if you have x, if you have y1, y2, you want to have something at the top. So just a kind of fiber product and a choice of component works in general. But if you want z smooth or normal, you need some existence results, but this is available. And from this, you can perform an inductive limit. So which E will be if T of X, and it will be the deductive limit of Y, where Y to X is a birational morphism with Y normal. I will also assume X normal, and we'll always change the border to this. And it contains, since it's a inductive limit of injection, it contains E of X. And when I have X to X prime birational map, then it induces X, U sub star a bijection from X to tilde X prime, such that it's sort of commensurate. U star of if X delta if without tilde X prime is finite. Basically, it's the number of curves that are contracted minus those which are contracted by the inverse. Typically, if G acts on a U in X, and it is by automorphism, then G results if U, which is a complement of a finite subset in X, and hence transfixes X. And it's also true, or if it's by pseudo automorphism, which means a birational map which is given by an isomorphism with f prime of codimension at least 2. So that's not so obvious to intuitive to have intuition what this beyond automorphism, because in the projective space it's automatically an automorphism, but in general that exists. But the point is that if we say this like this, there is a converse. If G if you have G X an irreducible variety and G acts by birational transformation, it transfixes of X if and only if there exists so G acting on X is conjugate G acting on Y with U, such that G, the action of G on U, an open subset, is by pseudo automorphism. And the point is that we can apply this theorem automatically when the group has property FW or distorted elements and so on. And that's the interest of this is that there is no assumption at all. Then its weakness is that it's like the first step of something better, but which is not obvious to carry over. And in dimension 2, there is we have classification and so on, and there is a much better conclusion, which is dimension 2. If G acts, so if G has property of W, and G acts on X by birational transformation, then G is conjugate to G acting on Y, which is projective as well, by automorphism. And actually plus, then there is a small list of possibilities. I can tell you it can go to P2, PGR3, P1, PGR2, of course PGR2, or irreducible surfaces. There is a specific list due to the fact that there is basically a classification of algebraic surfaces. So something which is not true, which is that's false in dimension 3. Because if you take SL3Z, okay, SL2Z, it acts on ABCD, acts on ZW by Z to the A, WB, Z to the C, WD. And that's just a formula for SL3Z that is similar. That's called the monomial action. And the monomial action of SL3Z on the C star to the cube is not conjugate to an action on the projective variety because of growth of the degree. But anyway, it could be true that in general you have if G has property of W, you always have a kind of an open or a model on some variety, not necessarily projective. And that's the idea that I had to iterate this procedure to smaller dimensional varieties. So far, I cannot do this. And the other question is that even in dimension 2, we have theoretically we have an action on a cantilever complex, but we would like to have subcomplexes that would be naturally defined. Like those with some vertices corresponding to varieties, some corresponding to smooth varieties, and we would like to have some geometry on this, but we don't know either. Thank you.
So this statement here is a consequence and refinement.
Yes, there is a lot of work to
pass from pseudo
the problem is
automorphism to true
that's
automorphism.
actually the main work is you have some also to go from an open subset to a projective one. There is a boundary, and you have to play on the boundary, and there is some good T hidden behind, and there is at some point you have this U and this Y, and there is a boundary which is just a complement. It's a number of curves. You change the boundary until you get some special kind of boundary, and
again, which statement is true in all dimensions and which in only 2 dimensions?
which is when it is false in dimension. So the statement that if a group of
It's the theorem general in all dimensions.
so there is no assumption of dimension here.
Yeah, but here.
But here dimension 2. So what I say that this is not true in dimension 3, but what could be true is this. What could be true is if I say that if G has property W act by birational transformation, then you can change the model so that there is an open subset on which it acts by automorphism. So say then if you don't need any reference to Y, just means there is a model, not necessarily projective, on which the action is by automorphism. So in the counter example I said with this R3Z, it's given with this model, which is a C star to the cube.
Do you have some cute examples?
So it's when you put rigidity action, it's true that some groups do not act in a way that you don't expect. So in a sense, it's to show that there are no examples. So in a sense, I would say for instance, that in the case of SL2, z square root of 2, it does not act in, it acts only in the way you can predict, for example, in dimension 2, whenever it acts, it goes through a morphism to an SL2. Essentially, it's a superpositivity result in that case, because you can, every action of SL2 square root of 2 extend to an action of SL2 or SL2 plus SL2 on the variety.
But then you mentioned like Hirzebruch surfaces.
Uh,
I think you mentioned Hirzebruch surfaces, right, at some point?
What surfaces?
Hirzebruch surfaces.
Hirzebruch, the automorphism group is essentially SL2, semi-direct something, and then the SL2, there is some room for groups with property at W. Basically, most of the surfaces do not have small automorphism group like virtually abelian or so, except a small number of exceptions, including Hirzebruch surfaces.
Do you have some statement for relative FW?
It was the implicit corollary of this theorem. I mean, if you can, this theorem applies to any group with property at W, and it also applies with, so if you have a larger group in which it, I mean, if you have a G with H, what can I say? You have G acting by birational transformation, then you know that H has relative at W, then you can apply this to X, to the subgroup. So every, for example, every distorted Z in a group of birational transformation is conjugate to a group of pseudo-automorphism.
Is this conjugation is for this subgroup action or a whole?
The consequence is for the smaller subgroup.
Ah, I see. Okay.
Distorted, this means that the degree was the degree of the iterated of your function that was so less than what expected. So if you have a birational transformation, you iterate it, you look at the degree. Does this distorted means that this degree was slower than what expected?
At this point, if it's distorted, you just know that it does not grow exponentially. But
That would be interesting, the converse.
yeah, but it don't. No, yeah.
You mentioned 2 it's equal.
It's
The same thing,
no, it's not the same. The elements of quadratic order, they are not distorted. They are distorted. So in dimension 2 is settled. In dimension 2, even this one, X. So this one with a unipotent matrix, so X, XY. Yes, it's undistorted. But it's not trivial at all, but it's not distorted in Cremona 2. It is distorted in Cremona 3. That's easy. So